Every single day, modern biochar production facilities convert over 100 tons of agricultural waste into a material that can remain stable in soil for thousands of years, while sequestering carbon and dramatically improving fertility. A single large-scale processing plant can produce enough biochar annually to lock away 30,000 tons of atmospheric carbon dioxide, while generating sufficient renewable energy to power 1,500 homes. How do these remarkable factories transform wood chips, crop residues, and forestry waste into a soil amendment so powerful that a single application can boost crop yields by 20 to 40% for decades? What industrial processes allow producers to capture carbon that would otherwise contribute to climate change while creating valuable products that regenerate degraded farmland? And why are American farmers, scientists, and environmental entrepreneurs calling biochar one of the most promising technologies for building climate-resilient agriculture while actually removing greenhouse gases from the atmosphere? Welcome to AgriCraft, where we explore the cutting-edge innovations reshaping American agriculture and rural sustainability. Today we are taking you inside the world of industrial biochar production, revealing the pyrolysis reactors, heat recovery systems, and quality control protocols that transform biomass waste into carbon-negative products. From sourcing diverse feedstocks, including forest thinnings and agricultural residues, through high-temperature processing in oxygen-starved reactors where ancient chemistry meets modern engineering, to screening facilities and packaging lines that prepare products for farms, gardens, and environmental restoration projects nationwide. We will show you every step of this revolutionary process. All will be revealed in this video. Biochar production represents one of humanity's oldest technologies rediscovered and refined for 21st century challenges. The fundamental process: heating organic materials in low-oxygen environments to create stable carbon-rich char, dates back thousands of years. Archaeological evidence reveals that indigenous peoples throughout the Amazon basin deliberately created biochar, mixing it with soil to build the famous terra preta, or black earth soils. These enriched soils supported dense populations and intensive agriculture in regions where natural soils are typically acidic and nutrient-poor. The terra preta soils remain remarkably fertile 500 years after their creation, testament to biochar's extraordinary persistence and beneficial properties. When European scientists first studied these soils in the late 19th and early 20th centuries, they struggled to explain fertility levels far exceeding surrounding natural soils. Only in recent decades have researchers understood that biochar's porous structure, massive surface area, and chemical properties create ideal habitats for beneficial soil microorganisms while holding nutrients in water where plant roots can access them. Modern scientific interest in biochar accelerated dramatically in the early 2000s as climate change concerns intensified and researchers sought scalable carbon sequestration strategies. Unlike carbon capture technologies that require expensive infrastructure and ongoing energy inputs, biochar production can be carbon negative, actually removing more greenhouse gases from the atmosphere than the process emits. This realization sparked a global research effort, investigating production methods, agricultural applications, and environmental benefits. Today, the United States biochar industry is experiencing rapid growth with production capacity expanding by more than 30% annually. Current domestic production exceeds 50,000 tons per year, with projections suggesting capacity could reach 500,000 tons within a decade as new facilities come online. The market value of American biochar production approaches $200 million annually. Driven by demand from organic farmers, regenerative agriculture practitioners, stormwater management projects, and carbon credit markets that compensate producers for verified carbon sequestration. International comparisons reveal interesting patterns in biochar adoption and production. Japan has used biochar-like materials for centuries in traditional agriculture, though modern industrial production remains modest. European countries, particularly Germany, Switzerland, and the United Kingdom, have embraced biochar enthusiastically with strong government support for climate-smart agriculture. Australia has developed large-scale operations focused on improving degraded soils in arid regions. However, the United States leads in agricultural technology innovation, developing continuous feed production systems and quality standards that are establishing benchmarks for the emerging global industry. One shocking fact surprises even sustainability professionals familiar with carbon sequestration strategies. A single ton of biochar produced from agricultural waste can sequester the carbon equivalent of removing nearly 2 passenger cars from roads for an entire year. When that same ton of biochar is incorporated into farmland, it continues delivering benefits for centuries, improving water retention, reducing fertilizer needs, and supporting beneficial soil biology. This combination of immediate climate mitigation with long-term agricultural enhancement makes biochar unique among carbon-negative technologies. The initial stage of biochar production begins with feedstock sourcing, the process of identifying, securing, and preparing biomass materials suitable for pyrolysis. Unlike many agricultural processes that require specific cultivated crops, biochar production thrives on diversity, accepting virtually any organic material as potential feedstock. This flexibility allows producers to solve waste management problems while creating valuable products, turning liabilities into assets. Forest residues represent one of the largest feedstock sources for American biochar producers. Modern forestry operations focused on lumber and paper production leave behind massive quantities of branches, tops, bark, and small diameter trees unsuitable for conventional wood products. Historically, this material was burned in slash piles, creating air pollution and releasing carbon dioxide, or left to decompose slowly, presenting wildfire hazards in fire-prone regions. Biochar producers partner with forestry companies and land management agencies, purchasing or collecting this waste material and transporting it to processing facilities. Agricultural residues provide another abundant feedstock stream. Nut hulls from almond, walnut, and pecan processing represent excellent biochar feedstocks, available in regions with intensive tree nut cultivation. Rice hulls, wheat straw, corn stover, and cotton gin trash similarly offer opportunities to convert crop residues into valuable biochar while addressing waste disposal challenges. Some producers focus entirely on single, abundant local feedstocks, building operations around reliable supply chains from nearby agricultural processors. Urban wood waste, including tree trimming debris, construction wood scraps, and yard waste, creates feedstock opportunities in metropolitan regions where landfill disposal costs incentivize alternatives. Municipal solid waste authorities and tree care companies increasingly partner with biochar producers, diverting materials from landfills while creating local green jobs and carbon sequestration benefits. These urban-sourced feedstocks require careful screening to exclude treated wood, painted materials, and contaminated debris that could introduce toxins into finished biochar products. Feedstock selection affects both production efficiency and biochar properties. Hardwoods like oak and maple produce biochar with different pore structures and surface chemistries compared to softwoods like pine and fir. Herbaceous materials, including grasses and crop residues, create biochars with higher ash content and different nutrient profiles. Experienced producers blend multiple feedstocks, optimizing mixtures that maximize production efficiency while creating biochar with properties matched to target markets and applications. Material preparation transforms raw feedstocks into forms suitable for efficient processing. Industrial chippers and grinders process logs, branches, and bulk materials into uniform chips, typically measuring between 1 and 3 inches. This sizing ensures consistent feeding into reactors and promotes even heating during pyrolysis. Oversized pieces may not fully convert to biochar, while undersized particles can create dust problems and reduce reactor efficiency. Moisture management affects both processing efficiency and energy balance. Feedstocks arriving at facilities often contain 40 to 60% moisture by weight, levels that require significant energy to evaporate during pyrolysis. Many operations incorporate drying systems that use waste heat from reactors to reduce feedstock moisture to 20% or less before processing. This pre-drying dramatically improves overall system efficiency, reducing fuel consumption and increasing throughput. Some facilities store feedstocks under cover for weeks or months, allowing natural air drying to reduce moisture without energy inputs. Sorting and quality inspection ensure feedstocks meet specifications and do not contain contaminants that would compromise finished products. Workers or automated systems remove metal, plastic, concrete, and other non-biomass materials that occasionally contaminate feedstock deliveries. This cleaning protects processing equipment from damage, while ensuring biochar remains free from pollutants that could limit agricultural applications or organic certification eligibility. The processing stage represents the heart of biochar production, where carefully controlled heating in low-oxygen environments transforms biomass into stable carbon-rich char. The fundamental process, called pyrolysis, occurs when organic materials are heated to temperatures between 700 and 1,800 degrees Fahrenheit in the absence of sufficient oxygen for combustion. Under these conditions, complex organic molecules break apart, releasing volatile gases while leaving behind carbon-rich solid residues with dramatically different properties from the original biomass. Modern industrial biochar facilities use sophisticated reactor designs that maximize efficiency, product quality, and energy recovery. Continuous feed systems represent the most advanced technology, processing feedstock in steady streams rather than batch operations. Prepared biomass enters reactors through airlocks that prevent oxygen intrusion while maintaining continuous material flow. Augers or conveyor systems transport material through reactor chambers where precisely controlled heating initiates and completes pyrolysis. Temperature control throughout the reactor determines biochar properties and production efficiency. Lower temperature pyrolysis, between 700 and 900 degrees, produces biochar retaining more volatile organic compounds and exhibiting higher cation exchange capacity, the property that allows biochar to hold nutrients where plant roots can access them. Higher temperature processing, above 1,200 degrees, creates biochars with greater porosity and surface area, properties that enhance water retention and provide habitat for beneficial soil microorganisms. Advanced facilities operate multiple reactor zones at different temperatures, optimizing conditions for specific feedstocks and desired product characteristics. Residence time. The duration material spends at peak temperatures affects conversion efficiency and biochar yield. Insufficient residence time results in incomplete pyrolysis, leaving unreacted biomass in finished products. Excessive residence time wastes energy without improving product quality. Most industrial systems maintain residence times between 15 and 45 minutes, balancing throughput against conversion efficiency. Computer controls monitor material flow rates and adjust heating to maintain target residence times as feedstock properties vary. Oxygen exclusion represents perhaps the most critical process parameter. If air enters reactors, feedstock will combust rather than pyrolyze, producing ash rather than biochar and generating excessive heat that can damage equipment. Industrial reactors use multiple strategies to exclude oxygen, including sealed chambers, positive pressure from steam or nitrogen injection, and airlocks at entry and exit points. Continuous monitoring systems measure oxygen levels throughout reactors, triggering alarms and automatic shutdowns if concentrations approach dangerous levels. Heat sources for industrial pyrolysis reactors vary by facility design and available energy resources. Some systems use external combustion of natural gas or propane to heat reactor chambers. Others burn a portion of the volatile gases released during pyrolysis, creating self-sustaining operations that require minimal external fuel once started. The most sophisticated facilities capture and utilize all pyrolysis gases, directing them to engines or turbines that generate electricity while providing heat for the process. This energy recovery transforms biochar production from an energy consumer into a net energy producer, generating surplus power that facilities export to electrical grids. Syngas, the mixture of carbon monoxide, hydrogen, methane, and other combustible gases released during pyrolysis, contains substantial energy content. Advanced facilities clean this syngas, removing tars and particulates, then use it in internal combustion engines or gas turbines driving electrical generators. A typical industrial biochar plant processing 100 tons of feedstock daily can generate between 1 and 3 megawatts of electrical power, enough to supply the facility's needs with substantial surplus for export. This distributed renewable energy generation creates additional revenue streams while demonstrating how waste materials can become valuable energy resources. Cooling systems safely reduce biochar temperature from reaction heat to levels suitable for handling and packaging. Direct water quenching, spraying hot char with water mist, provides rapid cooling but adds moisture requiring subsequent drying. Indirect cooling uses heat exchangers that transfer thermal energy to air or water without directly contacting char. This captured heat can warm buildings, dry incoming feedstock, or generate additional electricity through organic Rankine cycle systems. The most efficient facilities reject minimal heat to the environment, cascading thermal energy through multiple uses before final dissipation. Quality control throughout processing ensures consistent product properties and identifies problems before they affect large production volumes. Temperature monitoring at multiple reactor locations verifies that all material receives adequate heating for complete pyrolysis. Residence time tracking confirms that material flow rates remain within specifications. Automated sampling systems periodically extract small char samples during production runs, routing them to laboratory areas where rapid testing measures carbon content, ash percentage, and volatile matter remaining after processing. Finished biochar exits reactors onto cooling conveyors or directly into quench systems depending on facility design. At this stage, char appears as black, lightweight, highly porous material that crunches when crushed, revealing shiny surfaces that reflect biochar's crystalline carbon structure. The material retains the general shape of original feedstock, with wood chips producing recognizable char pieces showing wood grain patterns. This structural preservation helps identify feedstock types in finished products, an important quality indicator and marketing point for premium biochars. Post-processing operations transform raw biochar into products optimized for specific applications and market segments. Screening represents the first critical step, separating oversized pieces, undersized fines, and target-sized particles. Industrial vibrating screens with multiple decks simultaneously sort biochar into size fractions. Coarse materials exceeding target sizes can return to grinders for size reduction and reprocessing. Fine particles below minimum sizes have limited agricultural value but work well for water filtration applications or as soil amendment extenders. Grinding and milling create specialized products from screened biochar. Fine grinding produces biochar powders suitable for incorporation into potting mixes, compost blends, or animal feed supplements. Medium grinding creates granular products ideal for broadcast application using conventional agricultural spreaders. Some producers pelletize biochar, compressing powdered char with binders into uniform cylindrical pellets that resist dust formation and allow precise application rates. Pelletizing equipment borrowed from animal feed and wood pellet industries creates products that professional farmers and landscapers prefer for ease of handling and application. Washing may occur for biochar destined for sensitive applications including potting soils, hydroponic systems, or animal feed. Washing removes fine ash particles and soluble salts that could affect pH or introduce excess nutrients in controlled growing environments. Industrial washers tumble biochar with water, allowing ash and salts to dissolve and drain away. Multiple rinse cycles followed by dewatering and drying produce extremely clean biochars commanding premium prices in specialty markets. Inoculation and activation create enhanced biochars with superior performance characteristics. Some producers treat biochar with compost extracts, beneficial microbial solutions, or nutrient-rich liquids before packaging. These treatments inoculate biochar pores with living microorganisms or charge surfaces with nutrients, creating products that deliver immediate benefits when applied to soils, rather than requiring months or years for biological colonization to occur naturally. Activated biochars may sell for 3 to 5 times the price of untreated products, justifying additional processing investments for producers targeting premium markets. Quality inspection of finished products ensures compliance with industry standards and customer specifications. Visual examination checks color, uniformity, and freedom from contaminants. Biochar should appear uniformly black without brown or gray zones indicating incomplete pyrolysis. The presence of uncharred wood, rocks, metal, or plastic triggers rejection and reprocessing. Physical property testing measures bulk density, particle size distribution, and water holding capacity. Properties that affect application rates and agronomic performance. Chemical analysis quantifies carbon content, the defining characteristic of quality biochar. Premium agricultural biochars contain 70 to 90% fixed carbon by dry weight. Lower carbon contents indicate incomplete pyrolysis or excessive ash, reducing effectiveness and value. pH testing ensures biochar falls within acceptable ranges for target applications, typically between 7 and 10 for agricultural products. Electrical conductivity measurements reveal salt content that could affect sensitive plants. Heavy metal screening verifies freedom from toxic contaminants including lead, arsenic, cadmium, and mercury that could accumulate in soils and food crops. Surface area and porosity measurements using specialized equipment quantify properties critical to biochar function. High-quality biochars exhibit surface areas exceeding 300 square meters per gram, meaning a single handful contains surface area equivalent to multiple football fields. This enormous surface area provides habitat for billions of beneficial microorganisms and creates sites where nutrients and water molecules bind, making them available to plants over extended periods. Porosity measurements distinguish biochars with pore structures optimized for water retention from those better suited for aeration and drainage improvement. Packaging systems protect biochar properties during storage and distribution while presenting products attractively to retail and wholesale customers. Bulk packaging for commercial agriculture uses large woven polypropylene bags holding 1,000 to 2,000 pounds of biochar. These super sacks allow forklift handling and direct loading into application equipment. The breathable fabric prevents moisture accumulation while containing dust. For retail markets, automated bagging lines fill smaller bags ranging from 10 to 50 pounds, sizes suitable for home gardeners and small-scale farmers. Labeling communicates product specifications, application instructions, and environmental benefits to customers. All packages display guaranteed analysis stating minimum carbon content, pH range, and particle size distribution, along with manufacturer information and production date. Many producers include detailed application guidelines tailored to different crops and soil types, helping customers achieve optimal results. Sustainability messaging emphasizes carbon sequestration benefits and renewable energy co-production, appealing to environmentally conscious buyers willing to pay premiums for products with verified climate benefits. Bulk handling systems for industrial customers include pneumatic loading that blows biochar directly into trucks or storage bins. Some facilities offer just-in-time production and delivery, manufacturing biochar to customer specifications and transporting it immediately to application sites. This eliminates storage costs and ensures product arrives at farms in peak condition. Specialized application equipment has emerged, including modified manure spreaders and pneumatic broadcast systems that achieve uniform distribution across large acreages. Storage facilities for finished biochar must remain dry and well ventilated despite biochar's inherent stability. While biochar itself does not decay or degrade, moisture absorption can cause clumping and weight gain that affects application rates and equipment performance. Most facilities store packaged biochar in warehouses or under roof overhangs, protecting products from precipitation while allowing air circulation. Temperature control is unnecessary because biochar remains stable across enormous temperature ranges from Arctic cold to desert heat. Distribution channels connect biochar producers with diverse customer segments spanning hobby gardeners to commercial farms and environmental restoration projects. Direct sales through farm stores and websites serve home gardeners attracted by biochar's promise of improved soil health and reduced watering needs. These customers respond to educational content explaining biochar science and environmental benefits, often becoming enthusiastic advocates who share experiences through social media and gardening communities. Garden centers and nurseries stock bagged biochar alongside traditional composts and fertilizers, These retail partners need reliable suppliers, providing attractive packaging, fair wholesale pricing, and marketing support. Successful producers create point-of-sale displays with compelling graphics explaining biochar benefits and application methods. Staff training ensures salespeople can answer customer questions and make appropriate product recommendations. Agricultural dealers and farm cooperatives serve commercial farmers purchasing biochar by the ton for field applications. These customers make purchasing decisions based on agronomic performance data, cost per acre, and logistical convenience. Producers must demonstrate yield improvements and long-term soil health benefits through field trials and university research. Many offer soil testing services and customized application recommendations, positioning biochar as part of comprehensive soil fertility programs rather than simple products. Environmental contractors and municipal agencies purchase biochar for stormwater management, stream restoration, and contaminated soil remediation projects. Biochar's filtration properties remove pollutants from runoff, while its porosity enhances water infiltration and storage. These customers require products meeting stringent specifications for particle size, carbon content, and freedom from contaminants. Project volumes can be substantial, with single installations consuming hundreds of tons of biochar. But bidding processes are competitive and price-sensitive. Shipping logistics challenge biochar distributors because products are lightweight relative to volume, creating situations where trucks reach volumetric capacity before weight limits. This air freight effect increases transportation costs per ton compared to denser agricultural commodities. Successful operations build regional customer bases where delivery distances remain economical. Some establish satellite distribution centers in distant markets, shipping container loads to these locations, then making local deliveries more efficiently. Byproducts from biochar production create additional revenue streams that improve overall project economics. Renewable energy represents the most significant co-product for advanced facilities. Electricity generated from syngas combustion can provide 30 to 50% of total operation revenue, making energy sales critical to financial viability. Some facilities locate near industrial or institutional customers willing to purchase heat directly, using hot water or steam from biochar plants for building, heating, or industrial processes. Pyrolysis liquids, sometimes called bio-oil, condense from syngas during cooling and cleaning operations. These complex mixtures contain hundreds of organic compounds, including acids, phenols, and aromatic hydrocarbons. While not suitable for direct use as transportation fuels, pyrolysis liquids serve as chemical feedstocks for specialty applications. Some can substitute for petroleum-derived solvents, preservatives, or flavoring compounds. Research continues exploring methods to upgrade pyrolysis liquids into higher-value chemicals through refining and fractionation. Carbon credits provide emerging revenue opportunities for biochar producers participating in voluntary or compliance carbon markets. When biochar is incorporated into soils, the stable carbon it contains remains sequestered for centuries to millennia, creating permanent greenhouse gas reductions eligible for carbon offset credits. Third-party verification protocols confirm carbon sequestration quantities and permanence, issuing credits that producers sell to corporations and individuals seeking to offset their carbon footprints. Carbon credit revenues can add 10 to 30% to biochar sales income, significantly improving project economics. Environmental impact and sustainability represent core value propositions, distinguishing biochar from conventional soil amendments and climate mitigation strategies. Life cycle analyses consistently show biochar production and application deliver net negative greenhouse gas emissions. The carbon in biochar originates from atmospheric carbon dioxide that plants captured during photosynthesis. When biomass decays naturally or burns, this carbon returns to the atmosphere. Pyrolysis converts this carbon into stable forms that resist decomposition for centuries. effectively removing it from the active carbon cycle. Quantifying these climate benefits reveals remarkable potential. A single ton of biochar applied to soil sequesters approximately 3 tons of carbon dioxide equivalent when accounting for avoided decomposition emissions and reduced fertilizer needs from improved soil fertility. If American agriculture incorporated biochar on just 10% of cropland, annual carbon sequestration would exceed 100 million tons of carbon dioxide equivalent, roughly 2% of total United States emissions. Scaling to global agriculture could sequester multiple gigatons annually, making biochar one of few technologies capable of meaningful climate impact at scale. Soil health improvements from biochar extend beyond carbon sequestration. Research across hundreds of field trials shows biochar applications typically increase crop yields by 15 to 30% in degraded or marginal soils. Benefits include improved water retention, reducing irrigation needs by 20 to 50%. Enhanced nutrient retention minimizes fertilizer requirements and prevents nutrient pollution of waterways. Beneficial microbe populations increase dramatically, improving plant health and pest resistance. These agronomic benefits mean biochar investments pay for themselves through reduced input costs and increased yields even before considering carbon benefits. Water quality protection represents another critical environmental benefit. Biochar's high cation exchange capacity binds excess nutrients from fertilizers and manures, preventing nitrogen and phosphorus losses to groundwater and surface waters. Studies show biochar amendments can reduce nutrient leaching by 70 to 90% compared to unamended soils. This pollution prevention protects drinking water supplies and prevents algae blooms that create dead zones in rivers, lakes, and coastal waters. From sourcing diverse feedstocks that transform waste into resources, through precision-controlled pyrolysis reactors where modern engineering harnesses ancient chemistry, to screening facilities and quality control laboratories, ensuring consistent, high-performance products, industrial biochar production represents sustainable manufacturing at its finest. These facilities prove that climate mitigation and agricultural productivity are not competing goals but complementary objectives achieved through technologies that work with natural systems rather than against them. The future of American agriculture increasingly recognizes that soil health and carbon sequestration represent foundations of long-term sustainability and profitability. As regenerative practices spread, carbon markets mature, and climate policies incentivize emission reductions, biochar demand will continue accelerating. The production facilities scaling up today position themselves at the forefront of a transformation where agriculture becomes part of the climate solution, sequestering carbon while feeding the world. Thank you for watching this deep dive into biochar production and its potential to revolutionize agriculture while fighting climate change. If you found this exploration of carbon-negative technology and regenerative farming fascinating, please give this video a thumbs up and subscribe to AgriCraft for more investigations into innovations building sustainable, profitable agriculture. Leave a comment below sharing your thoughts on biochar or other climate-smart farming practices you would like us to cover. Until next time, keep exploring the technologies growing our regenerative future.